Okay, cool. So let me see if you're able to see the screen. Yes, yes, I'm sharing the right screen. So the last time, uh, before before our last meeting, and that would mean that was on Tuesday. On Tuesday, well, yes, we were trying to cover more about regression, right? And you might remember this slide where I was explaining that, and actually, let me use this little thingy here, where I was explaining that this place right here, this is the intercept, right? This is the height of the line, right? And we have a slope in our regression line. The slope is the rate of change, is how much the slope or how steep is the slope. Um, this is something that we call a linear function, and probably you remember linear functions from high school, right? I don't know if you did a lot of math in high school or not, but sometimes in high school they explain you a little bit of algebra and calculus, right? So as you might remember, linear functions look like this. They have an intercept and a slope. Of course, you could have a linear function without intercept, of course, right? You could set the intercept to 0, and then you could start right from here, right? Exactly at 0. That's also possible, of course, right? You might remember that. Um, but many times we want an intercept, right? We do want that. We want the starting point of the line, right? So I told you, and let me just go back and refresh what we explained or what we covered the last time. The last time we were covering assumptions, right? We were covering assumptions related to the linear regression, right, or the classical regression model. Um, and I told you that one of the most important assumptions is the assumption of normal distribution, right? It says that all these conditional distributions are normally distributed. Also, there is another assumption that says that the variance of these tiny distributions, the variance is the same, right? We expect to see constant variance across all these conditional distributions, right? Also, there is assumption that says that there is a linear relationship between all the means, right? There is a line, there is a linearity assumption that says there is a line, right? Is it low for you? Oh, let me check if I can check my microphone. Just 1 second. Yeah, sorry about that. Uh, Let me just check my settings. Is it still quiet? Okay, cool, cool. Thank you for letting me know. Let me just see. Share computer sound. No. Let me just stop sharing 1 second. I'm gonna pause the. Perfect. Now it's better. Okay, as I was saying, we were checking about assumptions, right? This is just a refresher of the previous lecture. Also, you have to, well, you don't have to, but it is important to remember that when you have a 0 here, right? When you have this type of function where my slope is multiplied by 0, that means that this intercept right here is going to represent the mean of y, right? So I explain you that when you don't have any predictor, that's what it means, right? When there is no predictor and we fit a intercept model only, the value of the intercept is going to be just the average of your outcome, right? And in fact, I gave you an example, I believe. Let me check. And the next slide right here, right? Also, remember the concept of residuals, right? Um, all this theory comes from the ordinary least squares estimation, right? And in here where we have the distance from the line of perfect fit, is what we call the residual. That's something that we cannot explain, right? That's something that the model cannot account for. So if this is the line of best fit, this distance is like taking a ruler and just estimating the distance, right? So the distance from this line is what we call the residual. So for example, this observation here is closer to the line of perfect fit. Therefore, this observation will have a lower residual. But this one right here will have a huge residual, right here. And that's okay. That could happen. The problem is when you have a very odd case, when it's very far from the line. So you should pay attention to that. Right? So in here, we were fitting a model. Well, oh, I forgot to tell you. Sometimes I'm going to say fit or fitting. That means that I estimated the model. It's kind of a word that we use when you're estimating models, but I want to try to avoid that. But that's why I use the word fit here. Um, it's something that we do a lot of times in statistics, but I should avoid that. Well, here we estimated a intercept only model. This is our words, the worst model that you can actually fit or estimate on your data, right? The intercept only model is just a model that tells you what is the value of the mean, right? There is no relationship between any other variable. That's why it's also named as the null model, right? It's just saying there is no relationship between anything with nothing. I mean, it's just the mean. But of course, what we want is to find a model that is better than this model. So many times, what we do is to add a predictor. So we, in this case, of course, in this example, we added age from the data set wage, and it showed that it actually is better because the p-value of the predictor is less than 0.005. Right? So the relationship between age and wage is not explained by chance. And this is how it looks, the relationship. Now, I told you about z-scores, and I don't know if I explained this point, if I explained the best I could this term, but the idea of the z-scores is to standardize your measurement, right? Your observed measurement. What you do is a transformation. So what we do is to take each value in my data set and then subtract from the mean. And after that, we divide that by the standard deviation of, uh, of the variable that we are interested on transforming, or the column, right? Because remember, we use data frames. So in data frames, each column is a variable. So what you do is to take one single cell from your column, and then you subtract that from the average of that column. And then you divide that by the standard deviation of that column. I should delete that. When we do this, everything, well, the mean is going to be centered to 0. And now you can speak about the values in terms of standard deviations. So in this case, h, well, the mean of h was 42.41, and now it's 0. And you could tell that the minimum value is minus 2.11 standard deviations below the mean. And the maximum value, for example, in this case, is 3.26 standard deviations above the mean. And if you do this, you can compare any variable. It doesn't matter the scale or the range of values in the variable. Now, let's pay attention to this. I didn't have time to explain this part the other day. So in here, what I did, and let me come back probably. Let me see if I show how I did it here. No, it's in the next slide. If you check my code here, what I did was to scale, well, the function scale is a function in R that you can use for transforming everything into C scores. You don't have to do it by hand. This function will do everything for you. So in this case, what I'm doing is creating a new variable called wage underscore Z, right? In my data set wage. And the new variable will be just C scores. Um, and also, H was already transformed into C scores or C values, right? When that happens, both variables are standardized, which is good, right? For interpretation, it's even better. When you do that, your intercept is going to be zero or very close to zero, like this in this case. I allowed R to show you how big, well, how small is the number, right? It has a lot of zero, 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 zeros. You can do that by using this option, sipen equals 9999. You will show the full number instead of showing the scientific notation, just in case you want to see the full number. I don't know if you want to do that. I don't like the full number because it's not very useful, but for teaching is fine. So as you can see, it's almost zero. It has 14 and 15 at the end, but of course you can round this to zero. So the intercept is now zero. Why it is zero? Well, because the mean of wage is now zero because we transform it into C scores. When you do that, the mean is going to be zero. Everything is going to be centered at zero. And remember that that the intercept is the value of x when x is the average. Well, in the intercept is the average of wage when h is equals to zero, right? And of course, given that h is also standardized, the mean is going to be zero, right? And so that means that the intercept is going to be zero, right? So we start from zero, which is kind of useful for interpretation sometimes, right? Not all the time. And now we have a slope, a estimated slope for h. And the number looks different. Let me show you how it looked like before. So when we were doing the, let me check here. When we first did the estimation of this model, this was the slope, right? 0 points, a rate of increase of 7.71 cents, right? So that was the rate of change. However, after standardization, look at the number. It's kind of different, right? Well, it's because it is now a correlation. It's not anymore a raw, a, how can I say, a raw covariance between two variables. It's now a correlation. Why? Because both variables, the outcome and the predictor, are standardized in, in the shape of a C score. So now what they represent is a correlation. So it's telling us that the correlation between H and wage is 0.19, right? So it's more useful sometimes because you can compare multiple variables at the same time. We're going to do that in the next assignment and also in the next practice probably. So you will have to compare which variable has a bigger weight on the explanation of your outcome. So in this case, of course, we don't have any other variable to use to compare, right? We don't have any other one, but we will in the next sessions. So now it's a correlation. And for example, let's imagine that you had any other variable. Let's imagine that, for example, you had another predictor like, let me see, mm, like, um, if you have a pension or not, right? Oh no, that's a very bad one. Uh, Um, Let me see something that is way more related to that and is continuous. Um, yes, number of kids, right? So let's imagine that you want to use number of kids as another predictor. How many children do you have, right? So that one could be also standardized. You could transform that variable into C scores because you want to compare the slope of different variables. And of course, number of children, number of kids, and age will follow a different metric, right? Or you could standardize that in order to simplify the interpretation of your regression model. Um, yes, practice number two should be there, Jennifer. Yes, yeah, yeah. Actually, should be there. I think I already assigned that one, right? Um, Let me double check that. I'm losing my mind. But yes, it should be there, I believe. All right. Hopefully that's kind of clear. Everything will make sense later once you kind of touch data and you compare different models. In this interpretation, well, in this case, the interpretation will be different. What we say is for one standard deviation increase in age, wage increases 0.20 standard deviations. That's how you interpret the regression when you are using C scores, right? This is something that we call a fully standardized solution. So that means that your outcome and your predictors are standardized. So it's a fully standardized solution. When we use Jamovi, and I'm going to show you later, in Jamovi, you don't have to do this. Jamovi will transform this into a standardized solution by just clicking one box. And you don't have to do this like we do it in R, right? We will see that later. Now, um, t-test is another model, and that one is actually nested into the regression model. In other words, t-test and linear regression are the same. The only thing that changes is the restrictions on the t-test. As you might remember, and let me just draw a picture here. In a t-test, what we have is, let me just do it here. We have a binary variable, right? It could be, for example, treatment and control group, right? We have this one right here. And we have a continuous outcome, right? That's the only thing we have in a t-test, right? But let's imagine that you want to add another predictor. Let's imagine that treatment and control is not the only explanation for your outcome, because sometimes you want to adjust your model. Why? Because, especially in psychology, because our experiments are not perfect. There is always something that might explain why um, my outcome is changing, right? And sometimes it's not because of my experiment, especially if my experiment is sloppy, right? Let's imagine that you did a very sloppy experiment. You didn't have time to assign people randomly to different conditions, or it was expensive for you to do it. So what you did was a quasi experiment. Quasi experiments are a relaxed version of experiments, right? Of the pure experiment. Quasi experiments are useful when you don't have money or you don't have time to actually do a pure experiment. So you do a manipulation, right? But you don't assign people to different groups. Or sometimes you don't do it because you cannot, right? If you are studying, for instance, the influence of smoking tobacco, right? You cannot make people smoke. They already smoke, so it's not a pure experiment. It's more like a naturalistic experiment in that sense, right? It's more like a quasi experiment. So let's imagine that you need to add another predictor here. So let's put a name to this example. So as always, I'm gonna call this depression. Oh, Jesus Christ, it's very hard to type here. I should use my tablet. I forgot to connect my tablet. So let's call it DEP. You may remember that this stands for depression. And then you have a predictor here, which is gonna be your grouping variable, right? So let's imagine you have a treatment and control group, right? You have your treatment group and your control group. So this variable is binary, right? You have only two options. You belong to treatment or you belong to control. Many times in the data set, it's going to look like a zeros and ones distribution, right? You will have zeros and ones. Zero if you're in treatment, sorry, one if you're in treatment, zero if you're a control, right? But there is something that we didn't account for in this experiment. What happens if the tendency to ruminate it's something that we need to control for, right? Because rumination is something that we do as a trait. It's something that you learned very early in your life, right? You learned to ruminate, but you didn't know, right? But you have to control the effect of rumination on depression because it's something that happens naturally for many people, but they don't realize. So, in order to understand if the treatment and if my treatment really works on depression, I should control the effect of rumination. So let's call this Rumi. I don't want to spell the whole word, right? So, and this is plus. It doesn't look like a plus, right? Let me make it better. It looks like a T, but it's a plus sign, right? You got it. So I need to control for rumination. And actually, I can do this in regression, right? I could add my binary variable and also a continuous variable into my equation. But in t-test, this one right here, is not possible, right? All the pluses here are zeros. Plus zero, plus zero, plus zero. That means that the t-test cannot handle multiple predictors. It can handle only one. And that one has to be a grouping variable, right? A binary variable. So regression is more powerful in that sense, right? Regression will allow you to add more variables that could be related to depression. So by adding rumination here, you are actually controlling the effect of rumination because you are taking into account the variants that rumination might explain on depression, right? Which is great. It's wonderful. That's why in statistics and science, we love regression. And we don't actually do a lot of t-test. T-test is useful for exploring different combination of differences between different binary variables. But at the end, what really explains the effect of your outcome is a regression model. And that's why I don't pay a lot of attention to t-test in this class. I always focus more on regression because regression is a way more improved model that will allow you to answer very complicated questions. And we don't have simple questions. We always have complicated questions because the human nature is hard to understand. So in psychology, what we have is models like this one, models like regression, right? Where you have multiple predictors. So, and also you need to take into account other factors, right? Not only rumination. Remember that some people have larger scores just because they were born as a female, right? So you would have to add here biological sex. Or it could be gender. It doesn't have to be sex, right? It doesn't have to be biological sex. It could be just gender. Because we also see an effect by gender. So we need to control the effect of gender. Why? Because we already know that people who identify themselves as females they tend to have a very, very high score on depression compared to those who are identify themselves as males, right? So that's something that we already know from literature. So we should control it. If you don't add these predictors to the equation, you might arrive to the wrong conclusion. And what would be the wrong conclusion? That your treatment is the only thing that explains the differences in depression. I'm sorry. I'm sorry. I told you I'm still a little bit sick. Um, and by the way, it's likely I can see now because of my health status that Thursday is going to be online too. So it's very likely. So be prepared for not driving to Stockton. Um, so yeah, it's going to be very likely online again. I'm feeling fine, but I'm still coughing a little bit, and I don't want to cough in front of you. You know, that doesn't sound healthy and sanitary. So I prefer to stay at home and don't put you in danger. Um, oh yes, of course I could, and actually I do. I'm drinking tea, hot tea, and drinking some, of course, hop syrup, and that helps. But yeah, I'm fine. I'm fine. It's just I have a lingering coughing. It stays for several days normally in my body. Um, so yeah, but I'm fine. I'm fine. So as I said, this is a better model, and I told you before in class when the semester started, all models are wrong, right? But other models are useful. So of course, the t-test is kind of a useful model, but it's wrong in the sense that it's assuming that the only explanation is a binary variable. That's silly to think about it, right? Especially in human behavior. In other fields, probably it's a good model, right? In other fields, probably if you have a good control of the environment in your experiment, a t-test should be fine. But in social sciences, behavioral sciences, and health sciences, we don't have that privilege, right? We need to assume that there are other variables explaining the effect of our treatment, right? So once we add this, we are sure now that the treatment is actually the explanation for the depression, right? Because you already added possible confoundings. That's how we call it. And actually, let me spell it out for you. Confounding. Count. It's a very weird word in English. Confound. That's you. Confounding. That's I. Uh, I don't know if that helps. Confounding. This is N. Well, you got it. So what it means is that there is another variable that could explain the differences that you observed and, by your treatment in control groups, right? Now, I haven't told you this probably, or I haven't told you this enough, but in the classical regression model, we don't assume anything about the predictors. I don't know if you saw the list of assumptions, but nothing, and well, anything is related to uh, uh, to the predictors. The predictors could have any distribution. So in my example here, right, in my example of depression by treatment and control, actually, let me go to R. Probably looks better there. I can explain that better here, typing. Make it bigger. So depression, as I said, could be explained by my experiment, right? An experimental variable. I said that it could be explained by rumination. And also, it could be explained by gender, right? Perfect. All these variables could have a different distribution. So for example, experimental could be continuous and normally distributed. Let's call it normally distributed. Let's imagine that it has a mean and a specific standard deviation. Let me just do it here. Right? Let's imagine it's just numbers. This one is the mean and this is standard deviation. Let's imagine that. Gender would actually be could be uh, a set of categories or nominal, or it could be a nominal variable, right? So gender could be, for instance, male, could be female, could be transgender, okay? Or it could be any other, right? So you have four categories, and still you could use it in regression. Let's add another one. What about if we add the number of times that the participant was hospitalized because of depression? So number of times at the hospital, right? Number of times could be number hospital, could be Poisson distributed, right? With an average of 5, right? So they have different type of values, right? The experimental variable, right? Oh, actually, I made a mistake here. I meant to write rumination here. That was silly for me. Rumination should go here. Rumination is a continuous variable. Gender is a nominal variable with male, female, transgender, and others. Right? Actually, here. And number of hospitalization is Poisson distributed, right? Yes, with a mean of 5. So yeah, regression doesn't care about the shape or the range of values of your predictors. What it really cares is about the conditional distribution of my outcome with all these predictors, right? That's what we care when we are doing regression. We care about the conditional distribution, not the individual distribution of these variables. And you might be thinking, why this guy is talking a lot about this? I mean, he has spent what 20 minutes talking about this. Well, I'm telling you why. It's because in psychology, especially, a lot of people believe that these predictors should be normally distributed. But that's wrong. I don't know how people started believing that, but it's wrong. They don't have to be continuous and they don't have to be normally distributed. They don't have to be any shape. You could use them whatever you want, right? Of course, there are some rules that you have to follow, but the distribution of these predictors don't matter, at least not for regression, right? So, and you will see this from other faculties, well, faculties everywhere, actually, not only in this university. You will see this in many places in the field of psychology, right? That they will tell you, oh, no, you cannot do that. You cannot mix continuous variables and nominal variables as predictors. You cannot. And it's like, why not? Of course you can. And you should, actually, right? So that's something that you have to bear in mind all the time, right? Um, and in other fields like geography, for example, I have seen the same mistake. In geography, the people who I have met before, and for some reason, they believe that they cannot mix different types of distributions as predictors, right? Different types of variables as predictors, which is wrong, right? And also they believe that everything should be normally distributed, like all these variables should be normally distributed. Also, there is another misconception about regression. The other one is that some people believe that the dependent variable should be produced by a normal distribution, which is wrong too. that the outcome or the dependent variable doesn't have to be normally distributed, right? It doesn't have to come from a normal process. What really matters is the conditional distribution of y given all my predictors. And we will see that later. We will see how we are gonna test the assumption of normality in my model, right? But the assumption of normality is not about the distribution of my outcome or the distribution of my predictors. Um, okay, you will see it later. Now, let's see this example. I have another example here. As always, you can check the code. Let me explain you what I did here. In the wage dataset, there is a variable called health insurance, health underscore ins. That means health insurance status. So in that data set, there are two groups, right? People who have insurance and people who don't have insurance. So we could ask the question, is the wage dependent on your health insurance status, right? We could think about it and probably we can test it out. So in this case, I did a t-test. Oh, a regression, well, it's the same in this case. I did a regression model. I'm not running a t-test, right? Why? Well, because it's the same thing. A t-test or a regression is exactly the same. So in this case, what we have is a slope of 27.92 and an intercept of 92.32. So how do we interpret this? Well, given that my only predictor is a binary variable, right? In this case, one means people have insurance, right? I'm going to call this ins. And two means, oh, sorry, zero means they don't have insurance, right? No insurance. So it's now a binary variable. You got it. It's very hard today to do that. When you do this type of regression, when you add this type of predictor that is binary, now the intercept is the mean of group zero. So in this case, this is the average wage for people who don't have insurance, right? And this is the mean difference. So this is the difference between people with and without insurance on wage, right? So on average, people with insurance are earning 27.9 more dollars compared to people without insurance. Well, that sounds like reasonable, right? Yeah, if you have insurance, you have a better job and probably you have a better salary, right? And probably the company actually covers the insurance here in the United States. In other countries, it's different. I wish it was different, but that's another political conversation for another type of class. But yeah, in here, what we see now, the intercept represents the average of group zero, and the slope, this little line here, represents the mean difference. And actually, let me see if I did the test for you right here. I believe I did it. But I did it in the next slides. I don't remember. I do many things in one day. Let me check. Let me just check 1 second. Oh, yes. Actually, see it next. Why? Ah, yeah, right here. Perfect. So the model that we just fed it looks like this. We have a y variable, which is wage. We have an intercept, and we have a slope, which is beta sub 1, right? The value for beta sub 1 is 27.92. And the value for beta is 92.31, well, 32, right? So we have estimated values now for these two parameters. And remember, this is a one possible outcome of estimated values. If you do the same experiment again, you will get a different, well, the same research, right? The same project, you would have different combination of values every single time. Remember, these are random variables. So this is what we did. And actually, it looks like a regression, right? T-test and regression are the same. When the variable has zeros and ones, like insurance status, we have two groups, right? The group zero is what we call a reference group right here. So group zero is going to be our reference group, and group one is going to be our target group. And you might be thinking, can I switch? Can I use, can I assign one to people without insurance and zero to people with insurance? And the answer is yes. You could switch it. It's totally fine. That would mean that you're using the other group as a reference. The difference is going to be that this number is going to be negative, but it's going to be the same number because it's a subtraction between these two groups, right? So yes, you can switch it. You just have to remember to have numbers in your coding, right? Especially zero is way more meaningful. And that's another thing. You don't have to use zeros and ones for the regression to make sense, but it's easier the interpretation when you use zeros and ones, right? You don't have to use zero. Some people might use one and two, three and two, and that's fine. That's fine too. But the interpretation is a little bit weird when you use very weird values. So the interpretation is easier when you use only zeros and ones. Believe me, this is the best way, and it will make your life easier. Um, and if you don't believe me, that's okay. You can try it by yourself. You can try different combination of numbers and come up with interpretation. Um, okay, let me show you. This is the average of group zero, the average wage, and this is the average wage for people in the group one, people with insurance, right? So look at the number. It's 92.32. And actually, it's the same number right here. It's the intercept. Now pay attention to this number right here. This is the average for group one. Now, if we do a subtraction, look at that. It's just a simple subtraction, right? The average mean of group one minus, sorry, the mean of group one minus the mean of group zero, it will give us 27.92, which is the same value that you see right here, right? If you don't believe me, you can do it by hand, and yeah, you get the same numbers. Now, another question that you might have in mind: why do I care about this? Why should we do a regression model if I can do this by hand? I mean, the model is answering what it can do by hand. I can do a subtraction, right? Well, there are many reasons. The first reason is that we want to estimate models because models will help you to estimate more complicated hypotheses. If you do it by hand, you cannot test any hypothesis, right? So the model is actually testing a hypothesis. The hypothesis is that the relationship between X and Y is not explained by chance, right? It's testing that, sorry, it's the opposite. It's explained by chance, right? So we are testing the null hypothesis that X and Y are not related. So of course, we can test a hypothesis. How? By getting a p-value. The other thing that is important is that now we are able to add multiple predictors by doing a regression model. In a t-test, we cannot do that. In a t-test, it's impossible. The t-test is a restricted model, right? We cannot do that. But regression is not restricted. You will be able to add multiple explanations that could be related to your outcome. And that's what we want in social sciences and behavioral sciences. We want to understand very complicated patterns of behavior, thoughts, uh, thinking styles, attitudes, right? Opinions. We want to explain that. And we need models that are more complicated, models that will have more variables that could be possible explanations, right? And of course, I'm doing this by hand and showing you a very simple example because there is something wrong about statistics. The way we learn, we teach it is that we always simplify the problems in order to make our idea a little bit clearer, right? But in real life, it's always more complicated. So, of course, this is a simple example, but in real life, it could get a little bit messy. Um, but if that happens, just send me an email, and I can help you for sure. Even if you get a job as a data analyst and you have questions, of course, you can ask me all the time. Um, uh, all right. Yes. There is something that I haven't explained here, and let me come back here. Um, I didn't explain you about dummy coding. Uh, when you have a variable and that variable has zeros and ones, we call it dummy. Um, and that name was coined in the context of transforming nominal variables into multiple columns. And we will do that as well in this class. But just bear in mind, just keep in mind that variables like these ones, zeros and ones, right, will be also called dummy coding or dummy variables or dummy distributed variables, right? About dummy in this case. This is how it looks right now, right? This is the regression that I just estimated on this data called wage. So we have people who belong to the zero group and people who belong to the one group, right? And the line, what the line is doing is just putting together two means, right? The mean of group zero is around here, and this one increases up to here, right? So it's like tying together two different means, right? That's what it's doing because I don't have a continuous variable. What I have is a discrete variable. It's a nominal variable with two levels, right? Zero or one. So the line looks like this. And what it's doing, this line, is actually quantifying the difference between group zero and group one. And at the end, what we got is this beautiful line telling us that group one uh, is getting more money compared to group zero, right? Because it starts at zero. So, well, it starts at this point right here, right? So this is the average. That is distance from here to here is the average of group zero, and then it increases to the point that these people are getting more money, right? This is how it looks like in a graphical representation. Okay, question, people, for you. Would you like a break? Would you like to continue? Should I continue? Or do you want a break? Denise says no break. Laila says break. Roseanne says break. Okay, well, I see more breaks compared to no break. Okay, so let's believe this is a democracy. So let's have a break. Let's have 10 minutes. And I come back at 11:05. Stretch your legs, drink some water, and I'll be very soon right here. Let me just pause our recording. All right. And let me open the chat right here so I can see. Oh, thank you, Mark. Hey, thank you so much for understanding. Um, so Let me see. Am I sharing? Yeah, I'm good. So I told you that the independent variables could have any distribution, any range of values, right? There is not any restriction on the shape or the distribution of your predictors. And actually, you could add uh, nominal variables that have multiple levels. Remember, nominal variables are variables that categorize things, right? They are labels. Like, for example, race, right? Race is a nominal variable because it has groups, right? And practically what you do is to assign labels to people. Some people, well, you don't do it, of course. People assign themselves a label in the case of race, of course. So you have white, black, Asian, or other in this example, right? This is from the wage dataset. So we have this nominal variable that we call race, and we have four groups. We could test if there are mean differences by race, right? We could see if race is explaining a difference on wage. But we have to do a little mathematical trick in order to do that. If you add this variable, and actually, let me see if I have it here, right here. If you add this variable as it is right now, right, this is the raw variable right now, the raw observation, R will, well, no, not R, the model will understand that this variable is continuous because it goes from 1 to 4, right? So what the model will understand is that, oh, so it goes from 1 to 4. So I'm going to assume there is some sort of continuous thing happening here. And I'm going to give you a slope that reflects that. And that slope is going to be wrong because this is not continuous. This is nominal, right? So it is not like answering 4 is superior to answering 1, right? Nothing is superior here. Nothing is, no, it's not even ordinal, right? It's not like white goes first, black goes second, Asian goes third, and other goes fourth, right? There is not any ordinal assumption on this type of data, right? So what should we do? Well, we should do something that we call dummy coding. We are going to transform this variable into three new dummy coded columns or variables in our dataset. And this is how it looks like. I'm going to use white as my reference group. And I'm going to create three new columns in my dataset. So one of the columns is going to be called black. So when people are black, or when they say they identify as black, they are going to be assigned to be number one. And if they endorse any other option, they're going to be zero. The same for Asian. If somebody says, you know, I'm Asian, that person is going to be one. Otherwise, it's going to be zero. And if that person says other, right, other racial membership or racial identification, that one is going to be one. Otherwise, zero, right? When that happens, white is going to become 000. That means that when a person, remember, each of these rows is a person. So this person right here, right, observation number one, let's imagine that, this person is white. How do we know that? Because she or he is zero on black, zero on Asian, and zero on other. Therefore, she or he should be white. That's the only option in this data set, right? Remember, we have only four variables. Only four groups: white, black, Asian, and other, right? So that's why we don't need to create another column for white. We don't need it because white is my reference group. Remember how we did it for the t-test, right? In the t-test that I showed you before, my reference group was people without insurance. They were the zero group. Now I have another zero group. In that zero group, is white. That's my reference group. So how does it look like? In my data set, you will see three new columns. Now, I have race. This is the raw column, the original column, and I transform it into three. I split it out into three different columns. So now I have a column for black, a column for Asian, and column for other. So if somebody says I'm black, that person is going to be 1. The other ones are 0 because they belong to another group. If you are Asian, you're going to be coded as 1, otherwise 0. If you are other, you're going to be coded as 1, otherwise 0, right? And actually, you can check it out, right? Look at this. This person is white, and she or he is a 0, right? The same for this one, 0, 0, 0 in all the options. That's my reference group. And you might be thinking, why do we have to do all this mambo jumbo thing, right? Well, it's because, as I said, the model is more like a robot. You know, that the models are robots. They they do a very good job. They will actually give you a number, but you have to make sure that the number makes sense. And there is another amazing scientist and researcher, Richard McElrath. He's at the Max Planck Institute. I admire him a lot. As he says in his lectures, the statistical models are more like golems, right? Like big beasts that will do whatever they are programmed to do, right? But you are the human being who drives these golems, these big robots, right? And if you add this variable as it is right now, it will give you a number, but that number doesn't make sense according to what you want to measure or you want to evaluate, right? Just delete this. Okay, now if you scroll down, you will see the regression that I did. So look at the model. Now the model has 3 new predictors because I have 3 new variables or columns in my dataset. I have black, Asian, and other, right? Remember, black represents 1 if you're black, 0 if you're other. Asian is 1 if you're Asian, otherwise the number is going to be 0. And if the people marked other, they're going to be 1, otherwise 0, right? So I have 3 new variables, right? But they are not exactly different variables. They belong to the same variable race. It's just a mathematical trick that we do in order to make sense of the regression line, right? Now, let's check the output. Let's see what we see here. Right now, we can see an slope for black, we have an slope for Asian, and we have an slope for other. What does this mean? This means that this slope is the mean difference when you compare black versus white. This is the mean difference when you compare Asian versus white. And this is the mean difference when you compare others versus white, right? And this is the average wage of white people, the intercept, because that's my reference group. So this is the average wage for white people. Now, let's see what happens here. Look at this number. The slope is negative. It means that black people are earning 10 point, well, almost $11 less compared to white people, right? Asians are actually getting more. they are earning 7.72 more dollars compared to white people. In this case, group zero, right? My reference group is white. And others, they are the worst compared to white people. They are earning minus $22.5 compared to white people. So they are the bottom of this ecosystem, right? And others probably, many of them are probably Hispanic, Pacific Islander, and other probably other ethnicities slash races, right? So probably they didn't ask specifically, or I don't know why the data set is like that. I didn't create the data set, right? But we can see the gap, right? And actually, this data is very accurate. This kind of, oh, just one thing. Remember, this data set has only males. It doesn't have females. So we don't know about females in this data set, right? And we have 3,000 males. So, of course, we cannot make any inference about gender gap or anything like that. Right now, it's just an inference about males, right? So, yeah, there is a gap by race, right? And we already know that. That's something that even replicates at the census level in the United States, right? Now, how do you know how many do-me variables you should create? Well, there is a rule of thumb for that. We use the rule k minus 1. That means that if you have 4 groups, you just subtract 4 minus 1, and you get the number of do-me variables that you should create, right? In this example, we have 4 groups, right? So if we follow the rule, it would be 4 minus 1. So that means that I need to create 3 do-me variables in order to avoid redundancy. If you create 4 do-me variables, you are adding redundancy to the model, right? That's why we need to follow the rule k minus 1. And that's why I created 3 groups, three do-me variables instead of 4 do-me variables. Hopefully that's clear, but no worries, you will have to do it anyway in your in the next assignment and practice. So again, if you don't believe what I said, what I did was to do everything by hand. Oh, thank you, Layla. What I mean is that if you add another variable here that says white, right? And the equation will transform the intercept into something else, right? So you will not be measuring the distance from any group. You will be measuring something that is not even interpretable, right? Because if you do that, if you add another white variable here, you are assuming that all these variables are independent, right? Like all these zeros and ones are actually independent of the other. So the inference is going to be inflated. So it's like assuming that this group doesn't belong to the same variable, this group doesn't belong to the same variable, and this group doesn't belong to the same variable. So the inference or the conclusion that you do out of the model is not the right conclusion. It just would be redundant, a redundant explanation. And actually the intercept would be, the intercept, I never done that, you know? We should do it and try to interpret the intercept, because the intercept would be if everything is 0. Yeah, it would be assuming that the intercept would be assuming it would be the average across across all the groups. That would be the intercept, right? Instead of being the average of the reference group. And when you interpret the slope of each group, you would be quantifying these as they were independent samples. And that would be crazy. Yeah, it doesn't make sense at all, to be honest. Um, I'm trying to think if there's any scenario where that could make sense, and I cannot think about right now. But I'm gonna do some research, because now that you are asking me about it, Laila, I'm thinking about if there is any context where we want to do that. I don't know. I haven't found it. But I don't know. Who knows? There might be something. But yeah, that's why I say redundancy. That by adding white here, the equation doesn't make a lot of sense, and you will inflate even the variance of your linear model, right? So yeah, yeah. Well, thank you, Laila, for the question. So as I said, in this part, I'm showing you um, all the parts that I just said here. So I estimated everything by hand, or quote unquote by hand, right? So what I did here was to estimate just the mean and the standard deviation of white people, right? And the mean is 112, 112.56, yeah. And it's the same number that you see right here in the intercept, right? So the intercept is actually the mean of of, of whites, right? And I estimated the mean of each group in this table, and I subtracted the mean difference, right? So what I did was to subtract 101.60 minus 112.56, and I got this number. And I did the same for Asian and other. And if you check the numbers, they are exactly the same as these numbers right here. Okay? So you can see it there. Okay. Again, you might be asking the question, why do I need to do this if I can do just a subtraction of means, just get the mean of each group and and just get a table like this one, right? Well, again, it's the same answer, right? We always want models that will help you to test hypotheses. If you do it by hand, you are not testing any hypothesis. You are getting an estimate, which is good, right? That's one step. You're getting an estimate, and the estimate is fine, but you don't know if that estimate is explained by chance or not, right? That's why we like models. Models will help you to get more information, right? And actually, models fit the data better compared to um, models, well, compared to estimations that are just estimations by hand, right? Also, and this is a simple example, right? In real life, you will have more predictors for a wage, right? So, for instance, you can add academic level and race at the same time. So, in that way, you are controlling and also adding uh, variance explained by other variables. So, for instance, here you would have, and actually have another example, or probably is in assignment number 2 very soon, I don't remember. You will have to do the same, but this time you will have to do it by education, by academic level, right? Let me check. Uh, Any questions so far? That kind of makes sense a little bit. Probably. Well, have you done this before in stats classes? No. Okay. Yeah, that's what I imagine. Okay, that's okay. That's okay. Perfect. That's good to know. That's good to know. So I'm not adding redundancy to your knowledge. Yes, and it is interesting and also a good tool when you want to do more complicated models. Okay, cool. As I'm saying here, this is boring, right? So we need to add more predictors. We need to add more possible explanations for our outcome. Um, and actually, we can, right? We could add multiple Dumi coded variables and also continuous variables. Why we can take other group to put into intercept? Oh, Jennifer, that's a very good question. Sorry about that. I didn't mention that. You could actually change the reference group if that's your question, Jennifer. Um, in this case, I'm using white as a reference group, but it could be any other group. It doesn't matter. I can use as a reference group other or Asian. And of course, the slopes are going to be different, but the conclusion is going to be the same, right? So if your reference group, let's imagine, is Asian, you would be subtracting the mean of black versus Asian, the mean of white versus Asian, and the mean of other versus Asian, right? So the numbers are going to be different, but the final conclusion is going to be the same, right? It's just you change the reference group and you will change the estimates, right? But the final conclusion is the same, right? And for example, if you use Asians as a reference group, and you will see the mean of Asians right here, and the numbers will change, but the conclusion is the same. Like people who identify as Asian are earning more money compared to people who are not Asian. Like that's gonna be the conclusion, right? If you change it. But yes, you can take any other group to put in the intercept. You are totally right, Jennifer. Um, Now, yeah, in this part, what I want to explain is what I already explained this, actually. I always go ahead of myself in these slides, but at least it's written here. So, of course, you can add multiple predictors, and we actually did it. We just did it. We artificially did it, if you can say that. Is the same variable, right? Is race, but it was split into different terms into the equation, right? That means that yes, regression is very flexible, and you can add multiple predictors at the same time. Let's see this example. This is an example with, and let me go to probably here. You can see here, I'm using the dataset rumination, and this data is on my website. You can just download the data, or probably you have it around there because we use it the last time. So in this equation, what I'm doing is predicting or trying to explain depression as a function of rumination and worry, right? So rumination and worry are my predictors. So now I have multiple predictors, but these ones are continuous. These are not binary or discrete, right? But I could do it. Actually, I could add another variable here, and that variable could be, for example, gender. In this data set, remember that gender has only two values, female and males, right? So I could add that variable right here, or I could add any other variable like region, SES, social economical status. I could add it too. I could add many other variables to the equation, right? But this time, of course, I added only two, rumination and worry, because we already know. Remember our plots when we were looking at plots and scatter plots related to depression, rumination, and worry, right? We already did that many times in our lectures, right? And we saw that, yeah, it makes sense to see a relationship between rumination and depression, in a relationship between worry and depression as well. In this example, I transformed the variables into Z-scores. Why? Because they were in a different metric. Remember that I explained you about Z-scores. So this is a good place to explain that as well. So the rumination score had values, I believe, from 0 to 30, and no, from 1 to 30, and worry was from 0 to 15. So the scale is totally different. So I had to do a transformation into Z-scores. The same for depression. I believe the total score, the scores in depression in this scale will range from 0 to 20, I believe, something like that. So yeah, they're totally different scales. So I transformed all these variables into Z-scores, right? It's easier to interpret the results when you transform it. And actually, that's how I created this beautiful 3D plot. You can also do it at home by using the package scatterplot 3D. Remember, if you see the function library at the top of my code, is because that's a package that I'm using. And most likely, you don't have it in your computer. If you want to run this code, you will need to have this package installed in your computer by using install.packages, or on RStudio, remember that you can install new packages by going in an easy way. You can go to packages on this tab right here, and then click install, and you type the package that you want to install. In this case, what was the name? Uh, Scatterplot 3D. So let's imagine you want to install that one. Scatterplot, oh, actually right here. Scatterplot 3D, and then you click install. And you do this only once in your life, and it's gonna be there forever, right? Unless you reinstall everything on your computer, of course, and you can delete it. But if you don't delete anything on your computer, it's gonna be there forever, right? I'm not gonna install this one again because it takes a lot of time. But I just wanted to reemphasize that you can install anything you want from my code, and you can also run the code in your computer. All right. In the future, I'm going to change this, of course, and I'm going to add a online path, so you don't have to download any data set. These are all the slides that I need to update little by little. It takes time to update the materials. All right. So let's see what happens here. We have two predictors right now. So that creates a 3D plot, actually. This is a scatter plot in a 3D way. Why? Because we have a more complicated relationship. We have two variables, and the normal Cartesian plane is not useful anymore, right? Because a 2D plane, of course, is useful when you have only one variable as a predictor and one dependent variable. But in this case, we have another one, right? So we need an extra dimension right here. And if you had multiple predictors, let's imagine you had on top of worry, you had gender, for example. Oh, that would make everything more complicated, right? Or if you had, for instance, stress, right? You will need a 4D plot because you are working now in a multidimensional space. So if you add more variables, it is more multidimensional. It's a what we call a multivariate space, right? So that's why we don't do plots when you have more than two predictors, right? It's difficult. There are some density plots that you can do with that, but you will need to render the plot with a sophisticated computer, and it takes time depending on how many observations you have. So, and the short answer is, well, no, you cannot. So this is the best we can do with R and Python and in other softwares right now. So let's make an interpretation of this. So look at the plane. Now we have a 3D plane. Remember, depression is our dependent variable. And let me actually try to center this a little bit. Well, let's do it again. So pay attention to the axis right here. Look at the y-axis. It has 0 right here, right? Remember, it has 0 because everything was centered at 0 because we are using z-scores. So the mean of depression is located right here. The mean of rumination is located right here. And the mean of worry is located right here at 0, right? So if somebody is located at -1 here in rumination, that means that that person has a score that is 1 standard deviation below the mean. If it's positive, it means that that person has a score that is located 1 standard deviation above the mean. So that person has a higher tendency to ruminate versus this person who has a lower tendency to ruminate, right? And the same applies for the other variables, right? People who are located in this side are are not worriers, right? They don't worry a lot, while these ones they worry more because they are above the mean. And the same for depression. If the observations are laying down around this area, of course they have a higher score of depression. But if they are below the mean, right, below 0, that means that they don't have depression practically. They have a very low score in depression. Now, let's make some conclusions out of this plot. Pay attention on how the plane is tilted a little bit, right? It's kind of, it's like these people have a bigger weight because this side of the plane is kind of going down like this. They have more weight. Why? Because this is a sample of healthy teenagers. They haven't been diagnosed with any depression symptom, right? They are just healthy teenagers. So that's why a lot of observations are in this area. People who are in this area are people who don't worry too much because they are -1 standard deviation below the mean, 2 or -3. They also are below the mean on rumination, and they also are below the mean on depression, right? Well, actually, I should draw this around here. These are the people who are doing better. They don't ruminate, they don't worry a lot, and they practically don't have depression. They might have reported like some symptoms of depression because they are teenagers, you know? When we are teenagers, life is so complicated and it's so dramatic that sometimes you can actually overestimate your feelings a little bit. You don't know how to estimate your feelings. You don't know how to feel it or how to interpret your feelings. So probably they were like overestimating something, but they don't have depression, right? But on the other side, we see the people who are more extreme right here. People who are very high on worry, they are in this area right here. They are on the area of high depression, and also they are on the area in the area of high rumination right here. So they worry a lot, they ruminate a lot, and they are depressed, right? So it makes sense that they are here. They are cases that are a little bit more extreme in that sense. They are not extreme cases, but compared to the average person, yeah, they are located right here. And as I said, we have like the average people here close to the mean, right? So those people are around here. These are the average guys in this data set, right? People who are around the mean of depression, around the mean of worry, and around the mean of rumination. So that's kind of the average of this. And as I said, it is tilted a little bit. It is kind of going down in this area right here. Let me just mark it probably with another color. This area right here, right? Because we really have a lot of healthy people. So they weigh more. And we don't have a lot. We don't have actually a lot of people with high scores on the three measurements that we are using in this plot, right? And remember, this is the result of estimating this model. What I did was to estimate this model, right? And the scatter plot 3D function will actually represent the line of best fit as a plane. So this plane right here that you see is actually the plane of best fit, right? Because we have a multivariate space with more explanations for your outcome. All right. Let me just clean the whiteboard here. That was a joke. It's not a whiteboard. I'm very good at jokes. Um, okay. Let me see if I have time for this. Oh, 11:30. That means that I have only 10 minutes. Okay, let me just explain this part in 10 minutes and I will let you go. All right. So remember that I told you that you have to standardize your X variables and Y variables in order to make a better better, how can I say, or improved interpretation, right, of the results. But there's another way to do that. You could standardize your estimate and not your model. You can take the estimate, the raw estimate from your model, and just change that into a standardized estimate. And that's what many softwares will do for you. R doesn't do it for you by default. And I love that. You might be thinking, why? Well, because actually in many applications, I don't need to standardize anything because I want to interpret everything in the metric that it was measured. So many times I don't need it, but sometimes I need it, depending on what's the aim of the analysis. If I want to compare which variables are superior to other variables in terms of explanation, yes, you will have to standardize that. But if you don't care about that, and what you care the most is about just to getting an estimate for each predictor, it doesn't matter too much, right? But this is one way you can do it. And, and actually, I'm doing it right here. What it means is that you take the estimate beta, right? The estimated beta, and you multiply this by, well, first you divide the standard deviation of x by the standard deviation of y, right? And then you multiply this by your estimated slope. And I made an example right here of that. So in here, in this example, I'm estimating this regression with a raw score. It has not been transformed, right? It only says worry and anxiety. So in this example, I'm explaining anxiety by worry. So what I'm thinking is that anxiety depends on worry, right? So anxiety was produced because people worry, right? And it makes sense too. Well, according to what I know, the little I know about psychopathology, that makes sense. Now, I could take the estimate and just follow this formulation right here. And I forgot to tell you that in R, asterisk means multiplication. Probably I didn't mention that before, right? So in R, this asterisk means multiplication. So what I'm doing is dividing the standard deviation of worry by the standard deviation of anxiety, right? And then I multiply the result by 0.14, which is the slope right here. And at the end, I get a standardized number. This number will go from -1 to 1, like a correlation, right? So what it's telling me is that the correlation between worry and anxiety is 0.48. Now, just one clarification here, one important thing. I'm saying this is a correlation because I have only one predictor. If you add more predictors, it is more like a partial correlation. We haven't studied partial correlation, and I don't know if we will have time, but there is also something called partial correlation. And if you add more predictors, that would be a different interpretation. But if you have only one, it's a correlation, right? Just a simple correlation. So the correlation is 0.48 between anxiety and worry, right? Because it is standardized. And you can do the same if you have multiple predictors. You can standardize your estimate without transforming your data into C-scores. But either approach works fine. You can follow the first approach, or you can follow this approach. The truth is that many softwares will do this for you, right? They will do this multiplication and division for you when you click on some options like Jamovi or SPSS or SAS or many other softwares will do exactly the same, and you don't have to do it by hand. In R, of course, you might need to do it by hand, or you can download a package that does it for you. I can show you some packages later that will create a that will give you actually there's one that I like. The package name is parameters, and it will give you the standardized solution by default. And probably I can give you some examples um, in the next practice. And well, yes, That was good. That was everything for today. Thank you so much, people. And thank you for being patient. And remember, our next class is going to be the same. It's going to be online. I'm still feeling a little bit under the weather. So yes, the next lecture is going to be online, fully online on Thursday. And we resume face to face the next week, just to make sure that I'm not going to pass to you any virus or anything. So also stay online if you have questions or if you need help with art or anything else. Please stay here and I can help you. Thank you so much, people, and have a wonderful, wonderful day.
When should we expect to see our